Imagine you are in the final, high-stakes moments of a tense multiplayer match, lining up the perfect shot. Suddenly, your screen stutters to a halt. Behind the scenes, your operating system decided that right now was the exact right time to install a mundane background security update. That lag happens because older, simpler operating systems relied on a first-come, first-serve rule. But treating every process equally based entirely on its arrival time is a poor way to manage limited computing power. Your game actively rendering frames is more urgent than an invisible software patch. To solve this, modern architecture uses priority scheduling. Instead of executing tasks in the order they arrive, the operating system assigns a numerical rank to every single task, prioritizing them by importance. This hierarchy is required for real-time operating systems, for multimedia playback, and hardware device drivers to function without crashing. When every task competes for the same limited CPU time, a system's ability to prioritize dictates whether it remains responsive or locks up entirely. Deep inside the processor's decision-making hub, every software process is tagged with a priority number before it is allowed to run. The numbering rule here is often counterintuitive. A lower numerical value represents a higher rank in the queue. Priority 1 executes before Priority 5. These ranks originate from two sources. User-defined priorities are set manually, like forcing a program to maximum speed in a task manager, while system-defined priorities are decided automatically by the OS. To calculate those system ranks, the OS evaluates hard metrics. It measures immediate memory requirements, its need to interact with hardware, and strict time deadlines. This dual input ranking allows the operating system to organize incoming tasks based on technical urgency and user preference. This timeline introduces three test processes, P1, P2, and P3, displaying their required burst time and priority rank. Under a non-preemptive model, the CPU strictly arranges them by priority number. The highest priority block completes its burst time uninterrupted, followed sequentially by the others. But for environments needing to react instantly to interruptions, systems deploy an alternative called preemptive scheduling. Here, process P1 is actively running. Preemption triggers when a new process, P2, suddenly enters the queue with a higher priority rank. The CPU immediately pauses P1, moves it back to the ready queue, and switches focus entirely to the new, higher priority P2. This interruption strategy reduces the response time for the system's most important functions. Preemption ensures that the most critical task always commands the processor, regardless of what was happening moments before. However, this strategy creates a vulnerability known as starvation. It's a scenario where low-priority processes are indefinitely denied access to the CPU. They get pushed to the back of the line and never execute. This happens because computer loads are constant. If a stream of new, high-priority tasks enters the system, they will endlessly preempt the queue, keeping the low-priority tasks waiting forever. A system optimized for importance can inadvertently create total gridlock for perfectly valid lower-tier tasks. Engineers resolve this with an algorithmic patch called aging, which tracks the time a process sits idle. Aging ties wait time to importance. The operating system boosts the rank of a process based on how long it has been waiting in the queue. Wait 10 seconds, and its priority number improves. This creates a mathematical certainty. Even the lowest priority task will eventually outrank everything else in the system, ensuring it eventually gets its time on the CPU. Aging ensures that while the system remains responsive to emergencies, background tasks are never forgotten. To explore how your machine juggles these algorithms, hit subscribe and click the link to the full OS playlist.